Hello, ECE 310 students. This is Dr. Vladimir Goncharov bringing you Lecture 3 of Week 13 in ECE 310. In this lecture, I will cover some topics from Chapter 6, Linear Shift-Invariant Systems, the responses, that is, the frequency responses of ideal digital filters, and difference equations, which is a discrete time version of differential equations. Let's look at linear shift-invariant discrete time systems. Well, regardless of whether a system is linear or not, or whether it's shift-invariant or not, a discrete time system will have an impulse response. You apply an impulse to the input, and the system being initially at zero initial conditions will then respond to that impulse only to give some kind of output signal h of n. So a sequence of numbers gets processed to produce another sequence of numbers. The first one only had one non-zero sample. Therefore, it's called an impulse. The output is called the impulse response. Linearity is assumed for what is covered next. And as you know, linear superposition is defined this way, that if x1 produces y1, x2 for the same system produces y2, then that same system will take a weighted average or a weighted sum of x1 and x2 to produce a weighted sum of y1 and y2, as you would expect, as if each one had been individually applied. So this demonstrates both the scaling and additive properties of linearity into a single kind of experiment called linear superposition. In continuous time system analysis, we talked about time invariance. With sequences of numbers, such as x of n and y of n, a different phrase is used. Instead of time shift, they simply say shift. The sequence got shifted. So we say shift invariant behavior of the system is a property that we also assume. What that means is it doesn't matter when a signal is applied, the system behaves the same way as it would have at the original time. If at some time here x of n gives y of n, then at some later time x of n minus n0 will give the corresponding y of n, but delayed, the same way that the input was delayed. So that means the system behaves the same way. It's not that we're demonstrating this by shifting the signal. So we're saying the system behaves, it's invariant in its response to the shifts of the signal. So we say shift invariant behavior. So now let's derive that a linear shift-invariant discrete time system has convolution property, just as the continuous time systems do. We have to bring up the sifting property of the Kronecker delta function. And here it's shown on the top line. X of n multiplies delta n minus n0, and then that is for each sample of the products of those two sequences. They're added up together to give some constant. Notice that the delta function only is non-zero for one value of n, so it doesn't matter what x of n is at any other value of n. It sifts out its value at n0, n equal n0. We can change the variables, replace n0 with n with n0, and you'll notice that delta of n0 minus n is 1 when the argument is 0, so it can be rewritten as delta of n minus n0 without any change. This has to do with the fact that it is, when time reversed, the same as before, if it were delta of n. So negating the entire argument gives the same result. We'll use this later in our derivation. So let's begin the derivation. It's quite simple. When the input is an impulse, the output is the impulse response. When the input is a delayed impulse, delayed to the right by n0 samples, the resulting output is the same impulse response, only delayed. So this is a result of the shift invariance of the system that we've assumed. The third relationship here is take the second relationship multiplied by a constant, that constant being the value that sequence X has at sample n0. The resulting output will be scaled by the same factor. So this is a result of linearity of the system. When you scale the input by some constant, the output scales by the same constant. Now, what we had as the last step of the previous slide now gets summed over all values of n0. And by linearity, the right side also gets summed over all values of n0. So you're taking a bunch of signals and applying them, superimposing them by adding them together to get the superimposed responses to each of those. This is again a function of the additive property of linearity. And then the thing I derived from the sifting property, now we can, as stated previously, replace that expression with x of n, and the resulting output on the right side you will recognize to be the convolution, the discrete convolution between x and h. So this is the convolution sum. And we've just proven that when you drive a linear shift invariant system with a sequence x of n, that the output y of n will be the convolution product of the input sequence x of n and the impulse response of that system. And using the properties of the discrete time Fourier transform, we know that in the frequency domain, the output spectrum will be the product, not the convolution product, by the multiplicative product of the two input spectra. I should say, of the input spectrum and the system transfer function, the Fourier transform of h of n. And as an aside, I'd like to mention that e to the j omega naught n sequence, where omega naught is a constant, is an eigenfunction of any linear shift invariant system. That is to say, when it is applied as the input sequence, the output sequence is the same thing, scaled by a complex, perhaps, constant. And that constant is independent of n. So we have a complex value scaling the same sequence coming out. And this then leads to a proof that a sinusoid in produces a sinusoid out at the same frequency, but perhaps a different amplitude or phase. No new frequencies are created when you're dealing with linear systems or linear shift invariant systems. Now for the first really confusing part of this lecture. Remember that we studied that discrete time Fourier transforms have periodic spectra. So, just as they have periodic spectra, the Fourier transform of the impulse response must be periodic. The ideal digital low-pass filter in the discrete time case will have a periodic frequency response. If you look at the period that's centered at 0, that is shown here from minus pi to plus pi, the period is 2 pi, that period looks like the ideal low-pass filter response in the continuous time case, a rect pulse, but now it's extended periodically by being convolved with delta sub 2 pi of omega impulse train. So we have to redefine our way of thinking about filters. A digital filter, that is, a discrete time system filter, will have a periodic frequency response, and only over one period will it be doing effectively a low-pass filtering. It is kind of confusing. So there is really no such thing as a low-pass filter in the digital domain, because everything has to be periodic. Look at one period only, and that's how you'll figure it out. Because in time, the sync sequence has a Fourier transform and frequency of a rect pulse that is extended periodically, the impulse response of the ideal digital low-pass filter is therefore a sync function. Here I show an impulse coming in and a sync function coming out. Well, I set it in a way that implies causality. One caused the other, but the sync starts coming out before the impulse comes in. The sync is extended for all time. Impulse is only located at one sample, n equals 0. So this system is not causal. It doesn't follow the rules of cause and effect, the way nature works, the way we observe it to work. So therefore, the ideal low-pass filter cannot exist. And we're processing sequence of numbers, so what we can do is kind of delay what we're doing so we can effectively look into the future and get around this limitation, but the delay may be intolerable. Here's a digital high-pass filter frequency response. Looking at only one period, from minus pi to pi, you see it blocks DC, there's nothing passing at 0, and then it passes the high frequencies above a certain minimum value, omega min. But then it repeats periodically, and that's confusing. So to keep things straight, draw the response over one period and then extend it periodically. It has the same form as we saw for continuous time. Ideal frequency, high-pass filter frequency response, that is, it's 1 minus the low-pass filter response. And just as I showed you in lecture, that if you take a wide pulse and subtract from it a narrow pulse, looking at only one period, you see the result. It's a bandpass type of response, but then extend that periodically, as must be done because we're dealing with periodic spectra. This is the ideal digital bandpass filter frequency response. So basically everything in chapter 6, everything in chapter 4 is kind of a periodically extended version of the spectrum obtained in chapter 5. Everything in chapter 6, periodically extended version of that happening in chapter 7. Now for a new topic, and the last topic, linear difference equations. This is the discrete equivalent of differential equations, and this is how filters are designed. So it's an important topic. In the previous lecture, we saw that circuits were used to come up with simple filters in the continuous case, RC, low-pass filter, etc. In the discrete time case, we don't have circuits. We have algorithms to process one list of numbers to give us another list. So case 1 is a way that a list of numbers may be processed to give a new list. And that is to take y, which is considered to be the present output value of our filter, and create it as a function of past and present input values, x. So x of n is coming in at, let's say, present time, giving us present time output y of n. X of n minus 1 is one sample before present time, so it's past time, one sample that happened, one sample ago, and so on. So you scale present time input by b0. One sample ago, you scale that value by b1, 2 samples ago by b2, etc. And what you have now is a weighted sum of x samples that can be expressed using a summation, and I show the summation ending at m. That is called the order of this filter. It's an mth order filter. And this is a special type of filter that has only input samples being considered to give us the output sample. Now you may wonder, what else is there? Well, you can feed back part of the output to the input, and that creates new possibilities. But this is the simplest case, and it's a little bit limited, but it has some nice features. It can be stable, guaranteed. It can give us the desired phase responses that we want, guaranteed, and so on. And very important to note that a system having this type of input-output relationship is causal. It does not look into the future, as the ideal filter did. And it's also satisfying of the rules of linearity and shift invariance. Here's an example that is a little bit confusing, so bear with me here. Let this difference equation define the input-output relationship of a system. That is, the output y of n is equal to x of n minus 2 times what x of n was 1 sample ago, plus 3 times what x of n was 5 samples ago. What is the impulse response of this system? So to calculate impulse response, you have to set x of n equal to delta function, and then plug into this expression. In this slide, I've repeated the question, and then below, here's a table. First column are the index values of n, second one, the input sequence, and the third one, the output sequence. The input sequence is a delta function, so note that it's only equal to 1 at n equals 0, and for all other values of n, it's equal to 0. Y of n, the impulse response, because this is a causal system, take my word for it, does not start responding until that 1 arrives at the input. So for all n less than 0, y of n is also equal to 0. As soon as that impulse arrives at n equals 0, the expression above states that y of 0 equals x of 0 minus 2x of minus 1 plus 3x of minus 5. All I did was plug in the value n equals 0 to get that statement. Now x of minus 1 and x of minus 5 are equal to 0, so they can be ignored. Y of 0 is equal to x of 0, so y of 0 here is shown also to be 1. And then if you plug in n equal to 1, n equal to 5, you'll also get two non-zero terms where the second and the third term kick in, but all the other output samples are 0. Then taking a look at the third column, I can express it in terms of delta functions. That 1 at n equal to 0 is delta of n. That 1 at n equal, or I should say that the minus 2 at n equal to 1 is minus 2 times delta n minus 1, etc. There are 3 non-zero points, and they each can be expressed as a shifted delta function scaled by a constant. Now let's go to a case 2, where the output, the present output, y of n, is a function of past and present input. Is a function of past inputs and outputs and the present input. Okay, well, take a look at those summations. The summation that involves the x terms, the first one, starts at 0. So that is, there will be a term in there, y of n is equal to b sub 0 times x of n. So it's directly a function of the present input. And then past inputs as well, because anytime n has something subtracted from it, you're looking back in time. Now, the second summation starts at 1. And that's because it's meaningless to define the, you don't want to have a circular definition here. If you started at 0, then you would have a y of n term on the right. You'd be defining y of n in terms of y of n. And that's just not done. So what you do is you say y of n is some function of the past outputs that have already been outputted, fed back, and processed to give us a present output value in combination with the input sequence x. So this is called a difference equation that it's still causal, but now involves feedback. It's causal because it does not look into the future, only looks into the past to give us a present output y of n. If you take the discrete time Fourier transform, I should have said discrete time in this slide, the dTft of both sides, you will get a summation of terms where the x of n minus k time shift is expressed in frequency as a scaling by a complex exponential. And then those x of e to the j omega may be factored out of the summation because it's not a function of k. Same with the y of e to the j omega. So simplification occurs in the frequency domain when we Fourier transform it. And then, after factoring out those spectra and taking their ratio, you get the transfer function of your system that implements this response. And it is expressed in the frequency domain as a summation of terms divided by another summation of terms, where those terms are complex valued typically. And I conclude this lecture with this one slide, which is a preview of what we'll be studying later. You'll notice in the previous slide, e to the j omega occurred a lot. And we can give it a label z. So e to the minus j omega k may be written as z to the minus k. That is e to the j omega raised to the minus k power. If you make that substitution, which is just a labeling operation, you'll see that in the numerator and the denominator, we have polynomials in z. Now, true, those z's are raised to negative powers, but we can we can say these are polynomials in terms of z to the minus 1. Or we can multiply numerator and denominator by z to some positive power so that all of those negative powers turn positive. But in any case, you get a ratio of polynomials in z. And difference equations therefore lead to what is called a rational expression for the transfer function. Rational means ratio, a ratio of polynomials. Extremely useful. This makes it possible to write algorithms, to build hardware to implement these filters using simple delay units and multipliers and adders. So it's an easy to implement, easy to analyze way of designing digital filters. Okay, that's it for this lecture. I'll talk to you later.